Okay, now on to chapter 9. So, with that, so the last couple of chapters we've been dealing with alkenes. Now we're going to talk about the triple bond version, which is the alkynes. So, like that. So these are actually going to be have analogous reactions, but lots of times they'll actually behave slightly differently. So that's what we're going to talk about, and then we'll get into one of the things that drives a lot of students crazy is talk about the synthesis reactions. So first off, right, with most things, we start talking about we have to do the naming, and with the naming, it's still this exact same thing with the same 4 steps, right? So the first step is always going to be find the longest chain, right, and then just like with the alkenes, it's going to have to contain the alkyne group, stuff like that. So, but again, you take you take the main chain, right, and to indicate there's a triple bond, you remove the A and E suffix and add Y and E. So for CC single bonds, right, it's A and E, right. So for double bonds, it's E and E, and it used to be historically, when they were originally coming up with the names, it was actually I and E for the triple bond, right. So AEI, but for whatever reason, this got changed to Y and E. I don't know why, but that's what they did. Stuff like this. So, but yeah, there was actually a process by which they did single, double, triple, A, E, and originally I, but then it changed to Y. So that's an easy way to remember it. All right. So remember, you have to do the side chains. Don't forget, we need to include where that alkyne is in the chain, right? So you can include that in quotes like that. So, but we don't have to put that in the name. That's what the Y and E is for. Right, so determine the attachment point. So you figure out which side is closest, which end is closest to the triple bond, and that'll be carbon 1, stuff like that. So and then you construct the name as normal, right? So just like you've been doing the entire time. So okay, so let's get a couple of examples in here, right? So bond. Okay, so here we go. So right, so here we go. So we need to find the longest chain, right? So 1, 2, 3, 4, 5, 6, 7, right? 1, 2, 3, 4, 5, 6, right? 1, 2, 3, 4, 5, 6, right? We can't do that because it doesn't have the triple bond. So it's got to be 1, 2, 3, 4, 5, 6, 7. Right? So here's our main chain, right? Like that. So 1, 2, 3, 4, 5, 6, 7, right? So it's C7, right? So normally it'd be heptane, right? But to indicate there's a triple bond, we remove that, and it becomes heptine. Okay, so we have to say where that alkyne is in the chain, right? So we need to figure that out, right? And then this side chain here, right? So remember, it's 3 long, right? So it's 1, 2, 3 long, right? But the problem is, right? It's not connecting at carbon 1, right? It's connecting at carbon 2. So it's not just a regular propyl group. That would connect here, right? This one is connecting at carbon 2, so it's a 2-propyl group. Sometimes some people call it an isopropyl group, and that's fine if you want to call it that. But I like 2-propyl because it sort of it's more descriptive of what's going on with it. So it's a 2-propyl group. It's 3 carbons long, so it's propyl, but it's connecting to the main chain through carbon 2. So that makes it a true propyl group. Okay, so this side is closer to the end, right? This side is closer to the end, or this end is closer to the triple bond than this end, so this is carbon 1. So it's 1, 2, 3, 4, 5, 6, 7, right? So the triple bond starts at carbon 2, right? And the 2-propyl group is connected at carbon 4, right? So here we go. We don't need to include the alkyne name. That's what the Y and E is there for. So the name will be, let's see, it'll be 4, 2-propyl, so like that. So 4, 2-propyl, so with that, 2 alkyne. Oh, not alkyne, heptine. Okay, so we have a main chain that's 7 long, right, with a triple bond in it, right? Well, where's that triple bond? Starts at carbon 2. Oh, hey, we have a 2-propyl group, right? Where is that connected on the main chain? It's connected on carbon 4, just like this. Okay? So. Forgot to turn off the okay, it's the last one here. So, okay, so now I will tell you that I forgot to mention this, so most triple bonds, actually, if you remember back, right, this bond is actually going to be 180 degrees. Right, so this is an sp hybridized carbon. So it wants to actually have a 180 degree. I show it like this, sawtooth, only because it helps to illustrate where these things are. It's a little hard to sometimes see where the carbons are, particularly on a skeletal structure without the dots. So with that, so I keep this up with the sawtooth just to make it illustrated. But in fact, it is actually straight. These compounds are straight. Like that, but I just do this because it's a little bit easier to see while you're learning, something like that. So okay, so here we go. So here's a compound, right? So 1, 2, 3, 4, 5, 6, right? 1, 2, 3, 4, 5, 6, right? So it's looking like 1, 2, 3, 4, 5, 6. So just out of tradition, I'm going to do the horizontal chain, right? So with that, so right, so we have 6, so it's C6, right? So normally be hexane, right? But since it's a triple bond, it's a hexine, right? So we're gonna have to say where that alkyne is, right? Right. But then we also have those two methyl groups, right? So methyl. Okay. So this end is obviously closer to the triple bond than that end, right? So it becomes 1, 2, 3, 4, 5, 6, right? So the alkyne, right? So the alkyne starts at carbon 1. Both of these are at carbon 5, right? So it becomes 5, 5 dimethyl 1 hexine. There we go. Now again, if there's a di here, even though they're connected to the same point, I need 2 numbers here, right? So if there's a di, I need 2. You can't assume that just because if there's only one number here, it's on the other one. You know, they're both connected to 5. I need 2 numbers here, right? So now, I will point out, I forgot to mention this before, right? Sometimes you'll actually see this dimethyl hex 1-ine. So this is a newer way of writing these. So I prefer this method mostly because that's how I was taught. But if you would write it like this to say like, okay, you know, to be closer to show where that triple bond is starting, that's fine. You can write it like this. I prefer this one, but it's really just your preference. So there we go. Okay, so how do we make these things? How do we make triple bonds? Well, if you remember back for these things, right? So to make double bonds, right? So we could take a halide group here, right? So like that. So if you had it, right? So in here, right? If you had a base, come in and grab that, right? This falls down, kicks that off. To go here, right? So the 2 electrons here actually form that second bond there, right? So you make H2O, right? Plus Br minus. Okay, so remember that's HOH. Always think of water as HOH. Okay, so if we want to make a triple bond, all we have to do is do this twice, right? So what we can do is if we have, right, so if we have this compound, right, and if we had base, right, we could just do it. We just put a whole bunch of base in, right? So the first one, right, comes in, grabs this one, that falls down, kicks this off, right, to form this molecule. that, right? That's just this. It's just, instead of just having hydrogen, we have hydrogen bromine, right? But what can happen again is if you have enough base in here, right? So you put in 10 equivalents of it or a whole excess of it, this thing can come right here, that falls down, kicks this off, right? And so you just do it twice. And so now you can sort of think of a triple bond as just two double bonds stacked on top of each other. So there we go. So we've made our triple bond. Okay, it's just this reaction twice. So like that. So, okay, so how do we make a triple bond, right? So if we have if we want to make it, if we want to go from a double bond to a triple bond, how do we do it? Well, it's not always obvious, but what you actually do is if you want to take a double bond to a triple bond, you actually first convert it, right? We saw this reaction before, right? So bromine, it'll add on either side of that double bond to go right here, right? And don't forget, there were already hydrogens here, right? Here and here, right? They haven't gone away. Now, if you add a whole bunch of base to it, right? This will come here, down, kick that off, right? You'll also grab that, collapse down, kick that off. There you go. So to go from double to triple, you actually have to go through the single bonded step, but you're putting bromines on either side, right? And with that, and you end up with throwing a whole bunch of this KOH, and you end up with a triple bond there. So this would be a nice scheme. So keep that in the back of your head. That if we want to go from a double bond to a triple bond, we actually go through this. You add bromine across it, and then that'll convert back. So, okay. Right. So if you want to do these, so the analogous reactions, right? So lots of times what happen is they'll just, if you're adding HX, so HCl, or HBr, or HOH, which is just water, or if you add, Br2, it happens the exact same way as if you would with an alkene, or if an alkene and alkane react the same, but the alkyne just adds twice, right? Something like that. So, right. So here we go. So you add, right. So if you had, right, this, right. So if we had chlorine across it, right. So first one goes on, right, and it just goes on a second time. Right, that was there before, right? You had, if you have excess of this, right, just add on some more, right? You add another set. That's it. Okay, so but if you have, right, so analogous reaction here, right? If you have HCl, right, first one's going to go, right? Hydrogen's here, right? So think about the mechanism, right there to there to there. That hydrogen's going to, hydrogen's going to add here, right? Positive charge is going to add there, right? Because this is the secondary, right? It's secondary as opposed to putting the positive charge there, which would be primary, right? So when we add this, right, when the chlorine comes in and attacks, it's going to attack there, put the chlorine there, right? But don't forget, we still have that double bond there, so it actually happens twice. And the exact same thing, right? So the hydrogen's going to add there because when you break, break this bond, right, you're going to put the carbocation there, so chlorine's going to attack here. So you're still going to follow Markovnikov on here, right? So, so you add HCl, HCl, HCl. You just do the exact same reaction twice. Okay. So, yep. Now the other thing that can happen is when you get to this step here, right, after you've added this one here, you've got the positive charge here. What can happen is you can actually get a resonance effect, right? So you've got a positive charge here, right? You've got lone pairs here, right? They're going to be attracted to that positive charge, so you're actually going to get a nice resonance structure where it looks like this, where those lone pairs can help out. Now the chlorine's not going to be happy because it's going to end up with a positive charge on it, but there is a nice resonance structure that can happen before the next chlorine comes in. So that can also actually help stabilize it. So, okay, now the same thing, right? So we talked about oxymercuration. We'll talk about oxymercuration and hydroboration, right? And they're actually going to work the same way, right? So for oxymercuration, right? So we put the OH, we add water, basically essentially water across it. But what happens is the OH goes on the more substituted side, right? The Markovnikov product, right? But the problem is, you do the same thing with with an alkyne, but you generate what's called an enol, right? The ene, so like that. So that mean double bond and ol, meaning alcohol, right? So like that. So an alcohol right on a double bond. When that happens, before another OH can come into play, it rearranges itself. It's what's called a tautomerization, and it swaps. It puts the double bond there to make the ketone. So like that. So this happens as soon as this forms. It snaps into this place here. Okay, so it's not just adding OH twice. It's you add it once, and that double bond rearranges to form that. Okay, yeah, I've got the mechanism here. It's a little crazy. It sort of cycles around, right? So essentially, what happens is the OH ends up here. The double bond goes down there, right? So like that. So it sort of cycles around, but the net effect is enols are not the most stable of compounds, right? So they actually prefer to be in the ketone state. So as soon as you form an enol, it'll snap around to the C double bond O form. Wherever that OH is, that's where the C double bond O is going to be. Okay, but same thing happens with the hydroboration, right? So you do hydroboration, right? You get the anti-Markovnikov product where the OH goes on the less substituted side, but the exact same thing can happen here, right? But instead, right? Remember, there's a hydrogen off of here, right? As soon as you form the enol, you put that double bond, C double bond O, where the OH originally was, right? So you end up, if you have a terminal alkyne, right? You end up you actually make an aldehyde, okay? So again, it's the same thing. You come in here after you form the OH, right? It tautomerizes around, right? So that collapses down there, that goes there, that goes that. But essentially what happens where that OH is, you now, the alcohol group that's where the C double bond O ends up being. Okay, so if you have a terminal alkyne, so one of the, sort of a double bond, a triple bond at the end, if you do the oxymercuration, right? So the OH is going to want to add to the more substitutes, right? So oxymercuration, it's going to want to add, right? This is the more substituted side, right? So that's where it's going to add. You're going to get this intermediate, but then that tautomerizes to form this, right? Where this alcohol group is, that's where the C double bond O ends up being, okay? The analogous reaction would be the hydroboration, right? Again, it's going to want to go on the less substituted side, right? So that's the primary versus, right? So this is a secondary, right? Because it has, assuming that's a carbon, right? It has 2 carbons on it. This one here is the primary, right? Because it only has 1 carbon attached to it, hydrogen on this side, right? So you get this intermediate, right? And wherever that C double bond O, or the alcohol is, that's where the C double bond O is going to end up. All right, so that hydrogen just becomes that one, and so where the alcohol was, that's where the C double bond O is. Right, so you get a methyl ketone versus an aldehyde. It's a nice way to make an aldehyde. Okay. Okay. Now, again, you can do, right. So if you have, so you can take a triple bond, right, and you can hydrogenate it, right, where we're going to take out, right. So remember with the alkenes, right, we just take them down to single bonds. With hydrogenation, right, you actually you add the first hydrogen, right, to make a double bond. Well, that's still reactive to this, right. So it goes ahead and takes. Reduces this triple bond all the way down. So you can't stop a hydrogenation at the step, right? It's just going to keep going, right? So okay. However, I should say a regular hydrogenation. However, what you can do is you can actually poison the system. Okay, and so a Lindlar catalyst, what happens is it's poison, so it's not reactive enough to do the second reaction. It's only reactive enough to make the to take a triple bond down to a double bond. It's not reactive enough to form this one. Now, so this is a way. So this is how you actually go from a triple bond to a double bond, and in particular a cis double bond. Because remember, the hydrogen with a hydrogenation. Remember the hydrogen atoms are poked in the same direction, and the molecule sits down on it. Right. So what's going to happen is the hydrogens are still going to add on the same face, on the same side, right? So that pushes everything else to the other side, right? So you end up, these hydrogens come from here, and they're going to go on the same side. So you end up with the cis alkene, right? So you go from triple bond to here, and it's just this catalyst isn't reactive enough to do it a second time. So this is how you make the cis product. Okay, if you want to make the trans, you actually go through this very crazy mechanism. So you actually put in lithium metal in the presence of ammonia, and it's really cool because electrons are flying out. They're getting chelated by the ammonia. And this is brilliant blue, this royal blue color. It's very cool reaction. But here, the mechanism is such that you end up actually getting the trans product formed. Okay, and if you want to see the mechanism, it's actually right here. It ends up being this, right? So the lithium is very electropositive, right? It wants to give away its electrons, right? So it very readily gives it away. So it gives one of the electrons to that carbon, and you end up, the hydrogen here on the ammonia ends up going onto these carbons, but it ends up being just these one electron processes. Something like that ends up going on, but the net effect is you get the trans double bond, right? Stuff like that. So. Okay, so if you want to go to just a single bond, right, you can just do a regular hydrogenation. If you want to make the cis double bonds, right, you do a Lindlar catalyst, a hydrogenation with a Lindlar. If you want to make the trans, you do the lithium. Okay, stuff like that. So there's the mechanism. Not that you need to know it, but there's the mechanism if you're interested. Stuff like that. Now we can also do. Remember, we were doing cleavage with ozone and potassium permanganate, right? We still get that, right? So we still get that molecular chainsaw, right? So C triple bond C, right? You still get that. You still get it cleaved, right? But the problem is you don't remember we were just adding, right? We were stopping at just the C double bond O. With the triple bond, you don't get that. You get full oxidation to the carboxylic acid, right? So these end up being right. So R end up being. You always end up with the carboxylic acid on either side of where that alkyne was. Okay. Now with terminal alkynes, what will actually happen is you actually end up getting with this formate product, right? So it just cleaves like it normally would, right? But it just so happens that that's an H here. This will actually get further oxidized because you put in a lot of this stuff. This will actually get hydrolyzed to carbon dioxide and water, right? So you make this ends up getting oxidized to carbonic acid, which ends up going up to static as CO2, right? So you actually only end up isolating this one side here. This one here would end up getting decomposed, stuff like that. But it's still the exact same product. It just so happens that this gets further oxidized, stuff like that. So, okay, so another important concept that we're going to need for later in this chapter, right, is the acidity of alkynes. It turns out that that the hydrogen here is actually pretty acidic for a carbon-hydrogen bond, right? So the pKa of something like methane, right, is a pKa of 60, right? It's really, really hard to pop off a hydrogen from a regular alkane. Alkene, not so bad. pKa of 44 was still really strong, but for an alkyne, it's actually only 25. Right? So if we throw in a base that has a pKa higher than 25, we can rip off that hydrogen. okay, and stuff like that to make this. Okay, and so what's really nice about that is that this is a really nice nucleophile. It's really small, right, and it can get in here, and you can come in and attack and kick off the bromine, and now you've made a carbon-carbon bond. Okay, that's the sort of that's a big part of organic chemistry, is making carbon-carbon bonds, right? So that's what we want to do. So we're gonna for a lot of this ways, if for the synthesis reactions that are coming out, if you want to make a carbon-carbon bond, the easiest way to do it, the way that you guys know how to do it, at least up to this point, is to take a triple bond, pull off that hydrogen to make what's called a carbanion, right? My carbocation had a positive charge, a carbanion has a negative charge, right? So that becomes a really nice nucleophile, right? And you can come in and attack a primary bromide to make a new carbon-carbon bond. Okay. Now, again, the stereochemistry is such that since it's we'll talk about this, the stereochemistry. What ends up happening is you get this transition state, and it ends up inverting the stereochemistry of this. Okay, so like that. So we'll talk about this a little bit more later. But essentially, what happens is it's like an umbrella popping open in the wind, right? Just kind of, an umbrella is like this. The wind hits it, and it pops like this. And it's doing so. If this was the R stereochemistry, what you would end up here would be the S. Okay, so everything inverts, right? So when you do this, but we'll talk about that more in the as the course goes along. So like that, I think that's next semester. Stuff like that. So okay, but again, one of the thing is this is a good nucleophile, right? But it really only works on primary bromides, but that's okay. Stuff like that. So for secondary and tertiary, we actually get what's called the elimination product. So it ends up actually, instead of adding here, it actually rips off a hydrogen here to make a double bond. Stuff like that. So really, you want to add just to primary bromides. Okay, stuff like that. So secondary and tertiary don't work so well. Stuff like that. So, but that's okay. It's still a good way of making a primary carbon. Stuff like that. So, okay. Okay. So again, this is how we're going to make carbon-carbon bonds. Okay, so next up. So this is one of those things that drives organic chemistry students crazy. Okay, but it is really the central theme of organic chemistry is how do we make complex products. And actually, what we're going to do is we're going to use what's called, at least to introduce this, we're going to talk about what's called retrosynthetic analysis. This is actually Nobel Prize winning stuff. So E.J. Corey at Harvard. This was this is what was stated. He's a big time organic chemist, like that. So, and so did he sort of helped pioneer this. Okay, and basically what he's doing is instead of starting at your reactants and designing forward, what you actually do is you design it backwards, and you say, how do I make that? And then sort of say, in order for me to make this, what do I then need to have? You sort of have to go backwards. Okay, so how do I get that product? That's what you're going to be asking. So what we're going to do is we're going to design the synthesis of this compound here, and we need to use acetylene, right? So with that, so C triple bond C, right? So with that, and any sort of alkyl halide, right? And I'll actually give you, when I'm probably done doing like an exam, is I'll show you an example of this. I'll give you a list of carbon bits that you can use to assemble together. Okay, so with that. But what's happening here is you say, instead of starting it here, you actually start here, and you say, okay, what I'm going to do. So the way this works, so above the line is sort of, we're going to talk a little bit about the general reaction, and then below this line, we'll talk about how it relates to the synthesis of the molecule for this question, right? So the first part is, right, so good rule of thumb for these synthesis reactions is the first part of the reaction is actually going to be assembling the carbon structure. The second part is manipulating the functional groups. Now it's a rule of thumb, so it's not an absolute, but that's probably where it's a good place to start. Okay, stuff like that. So think about the first half of the reaction is just going to be putting the carbon bits together to make the full backbone, and then the second part is going to be adding and figuring out how to do this. Like in this case, put on the alcohol group. Okay, so when we're doing synthetic, we're going backwards, right? So we have to think about that first. Okay, but we'll talk. I'll give you another example of that. Okay. Okay. So how do we make a primary alcohol? Well, we know this, right? Hydroboration, right? So we take some sort of a double bond, right? That's terminal alkene, right? So hydroboration, right, is going to put it on the less substituted side, right? So this is right. So this is right. So that's secondary carbon. That's a primary, right? So the OH, right, is going to go there, right? So when we do the hydroboration, right, it's going to end up like this, right? Well, that's probably what we're going to have to do here, right? But what sorts of molecule are we going to use to put this on there? Well, we can have, right, our full skeletal structure, all the carbon bits put together, and then the last step could be putting in that OH group, right? So we'd have to have the double bond there. Okay, so that it would go on the left substituted side. Okay, so we know what the last step is going to be. So now we have to focus on how do we make that. Okay, so for here, so how do we make an alkene, right? So we can use Lindlar, we can use, it's terminal, there's no sister trans that we have. You can use either Lindlar, right? You could use the lithium as well. But a good way of making a double bond, right, is just starting from a triple bond, right? Don't forget, right, we're going to have to use acetylene somewhere in there in our synthesis, right? So we're going to have to get to that stage at some point. Right, so let's take it here and then just do like a Lindlar and take it down to a double bond, right? So what we would need to make this, right, is just start with our carbon backbone as a triple bond and do a Lindlar down to a double bond. Okay, and so that's not so bad. Okay, so now we know how do we make that double bond, which then go on to put in that alcohol group. Okay, so the next question is how do we make that part? Well, for here, what we can do, right? So we're going to need to put carbon-carbon bonds together, right? So the way that we know it is to take some sort of, triple bond C, make the carbanion, right, and attack it to a primary bromine to make the carbon-carbon bond. Well, we can this carbon can be any size that we need to. Okay, with that, so from a list. So what we can do, right? So when you're designing these things, okay, so you know this part is going to be from the acetylene, okay, so that means you have to have a 1, 2, 3, 4, 5 carbon piece. So this, right, so this part here is here, and where this connection is, that's where the bromine is going to go, okay, so when you add this this component to it, right, it's going to add there and kick that off, right? So you have to be really careful with these things to make sure you get the carbons right. Okay, so with that, so lots of times what I've seen is you'll either add an extra carbon or you miss a carbon just because you're not keeping track, right? So 1, 2, 3, 4, 5, right? 1, 2, 3, 4, 5, and then your carbon from your acetylene here. I don't care if you do this sort of mixed sort of skeletal and this part. That's fine as long as you can keep track of what carbons are going on. Okay, and so what we need to do, right? So we have to use that. We know that's the alkyl bromide that we need to do. Okay, so how do we make this, right? So with that, so for that, right, it's just, we know how to do that, right? So it's take acetylene and add a really strong base, and so we add, the one we usually use is sodium amide. Okay, and so there we go. So there we go. Okay, so here's the synthesis, right? So we started from the alcohol, right? So how do we make the alcohol? Well, we start with the primary alkene and do a hydroboration. Okay, so how do we make a primary or a terminal alkene? Well, we take a terminal alkyne and just do like a Lindlar catalyst, right? Well, okay, so how do we do this? Well, there's the acetylene that we have to use, right? And so we can just add these other carbon bits as the alkyl bromide here, right? And then this will come in and attack. And then so how do we make that? Well, this we just buy out of the catalog, right? So, but how do we make that? Well, we take this and add sodium amide to go there. So this is how you can go it backwards, okay? And so here's the synthesis going forward, okay? So like that. So if you want to see it moving forward, it's just the exact same thing we did, right? Just going forward. Okay, so here's another one. Okay, so this is another way. So another way you can do it is that if you're getting good at this, right? So you can go forward. Okay, so like that, and that's fine. Okay, but you do have to just keep track of things, right? So, okay, so design to synthesis. Okay, so you can use the carbon atoms from this list below, right? And any other reagents you need, right? Any other non-carbon reagents that you need. Okay, and so here we go. So we have a right. So usually what you'll do, right? So okay, so typically what we're going to do, first thing you probably would want to do is just count the carbons, right? So 1, 2, 3, 4, 5, 6, right? So we have a 6 carbon piece, right? So with that, so what we've been seeing, right? And then so here, that's 2 carbon, 1, 2, 3, 3 carbon, 1, 2, 3, 4 carbon, 1, 2, 3, 4, 5 carbon piece, right? So we have a couple we have 2 carbons, 3 carbons, 2 carbons, 3 carbons, 4 carbons, 5 carbons, right? We don't have anything that actually has 6 carbons long, right? So we're going to have to snap 2 carbons together, okay? And so probably the way we're going to do this, right, is to either take, right? So we know we have to make carbon-carbon bonds. So we're going to have to use one of these C triple bond, or these alkynes, right? And make the anion and attach it to a primary bromide, right? So with that here. But which one is it, right? So how do we make, right? So we have, so we're going to use this, right? So it's 2 carbons long, right? So if we're going to do that, what do we have to add to it? Well, we have to add a 4 carbon piece, right? So if this is 2 carbons long, right, we're going to need to add the 4 carbon piece. If we were going to use, this piece, right? Right, this is C3, right? What would we have to use? Well, we'd have to add a 3 carbon piece. Okay, so here we go. So if we're going to use this one, right? So if we're going to use the 3 carbon piece, right? So if we were going to use, right, we were going to add the sodium amide, it would make that, right? Okay, so now we need to add that 3 carbon piece, which is here, right? So 1, 2, 3, bromide, right? We can do that. What would we get? 1, 2, 3, right? And then the C triple bond C, CH3. Okay, so we have 1, 2, 3, 4, 5, 6. Okay, here's the problem. Okay, we need to get this aldehyde group right at the end. It needs to be here. We don't have any way of doing that. Okay, and so this is probably not going to be the way to do it. Okay, so we can't do a three carbon piece adding in a 3 carbon piece. What we're going to actually have to do is use this 2 carbon piece and add the 4 carbon piece to it. Okay, and so here we go. So we take this, right? So you have our 2 carbon piece, right? We add the sodium amide. Oop, this is actually 2. Sorry. Right, and so this, since this is the 2 carbon piece, right, we need a 4 carbon piece. Like that. Okay, so here's our 6 carbons, right? 1, 2, 3, 4, 5, 6, right? We have a 2 carbon piece, 4 carbon piece, right? So this comes in and attacks there, kicks that off, right, to make one, 2, 3, 4. Okay, so 1, 2, 3, 4, 5, 6. Make sure you can count. You can count for all of these. Now the question becomes, okay, so now we've made our 6 carbon piece, right? So we have a 6 carbon piece. How do we make the aldehyde from this one here? Well, you have to think back to our reactions, right? So if you do hydroboration, H2O2. Remember you get this intermediate. But as soon as you make this, it snaps, it tautomerizes to, right, there's an H here, remember? H2, right, there's that H there. There you go. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, there's our product right there. Okay, so this way I went forward, right? But you have to think about how do we make an aldehyde on here. Now, there actually are a couple of different ways that you can make the aldehyde. There's a couple of different ways that you could do this. This is the way that this is probably the shortest way, but there are a couple of different ways where you could make the double bond and then slice it with ozone. You could make the C6 and then slice it with ozone, or excuse me, C7, slice it with ozone. That would actually be okay too. I would accept it because I don't care if it's a 10 step reaction, as long as every step is valid, it's fine. Stuff like that. But this is probably the shortest way to get there. Stuff like that. But there are other ways out there. Okay, just as a reminder, right? So about that. So why are we doing this, right? So this actually is what synthetic chemists do. Okay, they actually will come in, right? So if you're making, if you want to make this compound here, it's an alkaloid from a penicillium bacteria, right? So that's where it wasn't this one, but its cousin, right, produced penicillin. Okay, and so right, but this compound here, right? So it's a potential antibiotic, among other things. It's an alkaloid. If we want to synthesize this in the lab, right? So we talk about chemists will get around and think, how do I make this? What bonds do I need to make? Right. So here, right. So make this 5 carbon, right? So there's these 2 5-carbon rings here, right? So with that, and then making this 6-carbon ring here. And so what we can do is we can actually shift this 6-carbon ring up here, right? So with that, so to make the 5-carbon rings, right, we can actually start with a 5 and a 6, right? And then crimp them together. Basically, connect that carbon with that carbon there, right? So like that, so connect it to make the 5,5 spiro compound there. Well, how do we make that? Well, we can essentially add this part to it, okay, to make this slightly smaller one, right? So, and also take the amine down to there, right? So like that, and then you can snap these things together like this. And then how do we make this? Well, we can make that from proline. And you think, how then, blue blazes, there's no way that you could think about starting with proline and going all the way up here. But it actually does make a little sense, because that ring there with the right stereochemistry is actually that ring there. Okay, and so they actually go through this. Chemists will actually go through this process, right, to break it down to know where to start the starting materials. You may end up starting with 1,000 grams of this, and then go through all of these reactions, right? There's a lot of reactions involved, and may only end up with a couple milligrams of this, but that's okay if you're just trying to make this in order to evaluate it. Okay, and part of the problem is, part of the this work is to go through the mental exercises and develop new chemistries to be able to design these things so that for other compounds, it can be useful. Okay, so I don't want to say that. I just want to point out that this isn't just some sort of completely academic exercise. There actually is, chemists do this. They sit in a room, and if there's a reaction that's problematic, I've been in these rooms, and you'll discuss, and people come up with different ideas for how to do this, because everybody can kind of approach it a little different ways. Okay, so with that, so that's what we got. So with that, so good luck. These synthesis reactions everybody struggles with them. Okay, it's a little bit of an art to doing this. Okay, and so the best way to do this is to practice, stuff like that, and to just see, get into see what the groove is. It's usually the first part of the synthesis is going to be putting the carbon bits together, right, and then the second part is going to be getting the functional groups correct. That's not always how it is, so be careful. But when in doubt, think of it that way. So with that, particularly since you don't have that at this point, you don't have it may seem like you have a lot of reactions available in your arsenal, but you actually don't, and so you can sort of take advantage of that. Like that, but just get it, just start working away, and certainly come see me if you're having issues. So good luck. So with that, and start working on the homework.